A fair die is tossed 360 times. The probability that a 6 comes up on 70 or more of the tosses is greater than 0.5, between 0.16 and 0.5, between, and so on and so on. Okay. So obviously the probability that a single roll is equal to 6 is 1 in 6. So the probability of success is a sixth. Probability of 7. Oh. We need is there a way that I can just immediately rule the answer is A or E quickly here? So, in fact, the answer is, ooh, is the, oh. Right, we're looking for 70 out of 360 successes, which is a little bit greater than 1 in 6, right? This is, it's approximately 1 in 6, but it's a bit greater. In fact, it's 1 in 6 plus 1 in 36. Okay, so the probability, let's let S be the number of successes, or the number of sixes out of 360 rolls. Probability that S is equal to K is and let's let 360, let's let that be equal to N. I think it is N choose K times 1 in 6, 1 over 6 to the power of, well, there's a 1 in 6 and there's a 5 over 6. One of these is raised to K and one is raised to N minus K. I suppose this is K and this is N minus K, right? I think the answer is just A. Like, kind of because of this, right? You expect, the expected number of sixes is 60. So with 360 tosses, there's a pretty good chance well, no, it could be greater than 60 or it could be less than 60, right? So maybe the answer is B, between 0.16 and 0.5. I don't have I don't know what the best way to work out some kind of approximation to this is, but like is there a central limit theorem thing we could do here? Like, what is the distribution of the number of rolls going to look like? Something like this, right? Where, what is the peak going to be? Is the peak at 60? Probably, right? Well, no, maybe not. I don't know. What is the most likely number of rolls, or most likely number of sixes? Well, 60 is close to this peak. This is certainly the expected value, right? I'm not claiming that this is the mode. I'm not super confident here. Like, so this will probably be S is equal to K. I hope that this is correct. We would have to add this up for K greater than or equal to 70, all the way up to 360. But I don't think that's really what is intended to do here. What if we instead thought about like a coin toss, right? A coin is tossed 360 times. The probability that heads comes up. Now the 70 we should change to something more fair. Let's make it like 190 or 200. 200 is a bit extreme. Let's go 190. The probability that heads comes up 90 times, or 190 out of 360 times. It's not greater than a half, right? It has to be less than a half, but not that much less than a half. Like, it's not going to be out of the realm of possibility that you see like, we're not deviating from the mean that much. I'm totally not confident on this. But, you know, just based on the magnitude of these numbers, you know, if you rolled this die 360 times and you saw it come up more than 70 times, a 6, like, you wouldn't be surprised. You wouldn't be like, that's unreasonable. But between 2% and 16, I don't know. This is not a confident answer at all, and I'm not even sure what the most reasonable way of solving this problem is. Maybe just approximate. I think maybe like approximating the distribution with a Gaussian, and you know, normalizing things, figuring out what the standard deviation, like where 70 lies, how far away is 70 from the standard deviation, and kind of estimating from there. But this is what I would answer if my life didn't depend on it. If I have more to say, I'll put it down in the description. Thanks for watching.